Hey, Nicolas Février here. I'm a TME for the Service Provider Business Unit in Cisco, working on the NCS 5500 family. We are trying something new today, and it could help you reducing the time needed to adopt our technology in your networks. I'll tell you more just after the intro. Our customers are asking for validation in multiple situations, before selecting a new product or a new vendor, and before inserting a new version or a new product in their network. In certain cases, the lab required to perform specific tests is too complex or too large. So we want to run this test ourselves, record the output, and present the results under the form of videos and blog posts. For example, if you need to perform a traffic load balancing test on a very large bundle, or if you need to create a snake made of dozens and dozens of 100 gig interfaces, it's not something trivial to set up. In some other cases, you may want to verify the redundancy of the route processors, the system controllers, the fan trays, the fabric cards, or you want to understand the packet processing and the packets per second capability of the box. So basically, the first goal of these videos is to save you time and resources. But even if you are not directly interested in the test, with the comments that we will add to the results, it will give you additional details on the products. So it may be of interest for a population of network engineers looking for more details on the router's internal mechanisms. In the description of this video, you will find the link to our xrdocs.io page where all the tests will be listed. Some videos will contain a single test, some others will contain many, so we'll add shortcuts to go directly to the right section. Finally, it's your chance to ask for specific test cases. Please use the comment section and let us know what will be of interest to you. You know the drill. If you want to be informed of the next publication, click on the subscribe button and the bell. Also, you can follow us on Twitter, Cisco iOSXR, and XRDocs. See you very soon. Hello! Today we'll talk about a common misconception related to the merchant silicon chipsets, the programming speed. How fast can we program the route in NCS 5500? How does it compare to custom silicon? Common questions we will try to answer today. If you read the XRDocs publications and watched the videos, you certainly know that the NCS 5500 is based on a forwarding ASIC coming from the DNX family. For this demo, we will use a Jericho Plus chipset with an external eTCAM. And since we are using iOS XR632, it will be very easy. All routes, both IPv4 and IPv6, will be programmed in the external eTCAM. We can store 4 million entries and even more, so we have plenty of space. The device on the test is a chassis, 8-slot, and we are using a 36 ports 100 gig Scale line card. We generate 1.2 million IPv4 routes from another router through a BGP station. So the idea here is to set up something realistic even if we are performing the test in the lab. So the prefixes are coming from a real router and not from a traffic generator. Quick look before starting the test. We see just 4 routes in BGP and 59 entries in the external eTCAM. We are using telemetry to stream the ASIC and the BGP protocol statistics, and the frequency or the cadence that we will use for the streaming is 1 second. Now we unshut the session from the neighbor and take a look at the DUT. The prefixes are being learned from this BGP peer, and they are also programmed in the 4 NPUs of the line card. You can see the route on this graph, the dashboard we use here in Grafana. Now that everything is programmed in hardware, we can have a closer look at the graph. We identified 3 key moments here. Number 1, the moment we receive the BGP routes and start programming the ASIC. The second moment is when we receive the last BGP route, that's 9 seconds later. And the third and final moment we will look at is when we program the last route in the ASIC, and that's 41 seconds since the first route has been received. Based on these numbers, with a simple math, we can derive the programming speed. The BGP routes are learned in the route processor at 133,000 prefixes per second, and they are programmed in the hardware at more than 29,000 prefixes per second. To give a point of comparison, that's faster than ASR 9K with Tomahawk line cards. Also, we can perform the opposite test. We shut down the BGP session from the neighbor and check how fast the routes will be flushed. So we withdrew 240,000 entries per second from the route processor memory, and we flushed more than 34,000 prefixes per second from the ASIC table. Multiple internal improvements have been added to optimize the programming speed in these ASICs. And you can see that indeed the results are not different from what you could expect from a custom silicon device. More technical details will come with the blog post linked to these videos. As usual, don't hesitate to post comments and questions. Also, if you want to see specific topics covered, please let us know. Thanks a lot for watching. See you soon. Hello! In last video, we talked about the FIB programming speed on NCS 5500, and we picked a line card with Jericho Plus with external eTCAM. In the blog post comment section, we got this question, wondering what the FIB programming speed is the other way for the 5501-24H, as it doesn't have an external eTCAM. Maybe it's faster? Let's try to answer this one. First, a quick reminder on the key components of an NCS 5500. We have Jericho and Jericho Plus ASICs, and FE3600 to interconnect them. The 55A1-24H uses 2 Jericho Plus ASICs back-to-back, no external eTCAM, no FE3600. We have 2 types of Jericho Plus ASICs in our products, and the big difference between them is the LPM database size. In this 24H router, we use the largest version that can handle more than 1.5 million v4 routes. So we have 2 databases, here LPM and LEM, and we will sort routes in one or the other depending on the prefix length. For our demo, we will reuse the same testbed, but this time the routes will be injected from the 5508 to the 24H. Let's check the router first. We verify we have the BGP session in active state because it's admin down on the other side. Victor built us another Grafana dashboard, and we can measure BGP routes in RP and entries in LPM and LEM in real time. For this test, we'll run IOSXR 651. Okay, let's get started. On the 5508, we remove the shutdown config from the BGP peer. The BGP is now established. We will restart receiving the route on the 24H. It's reflected via telemetry every second. Now that all the routes have been received on the system of the test, we can check the prefix distribution between LEM and LPM, and we can see that it's more or less half and half for the internet table. Using telemetry for this test is convenient because it gives a very graphical view of the programming speed. We start receiving routes at 23:49, and we have everything programmed at 24:20. That's 31 seconds later. Quick math, it's 24K prefixes per second in LEM and LPM. Also, for the BGP route in the route processor, we got everything at 23:59, that's 10 seconds after the beginning. So it's 75,000 prefixes per second. Like we did last time, we measure prefix withdrawal speed 2 simply by shutting down the session from the neighbor. we measure 26 seconds to flush all the routes, which represents almost 29K prefixes per second. To conclude, here are the results of the programming speed for eTCAM and internal memories. It shows that eTCAM is actually slightly faster. Hope it answers clearly the questions. Don't hesitate to post all the comments on the video or the blog post. Thanks for watching and see you very soon. Hey, my name is Nicolas Février and I'm part of the TME team in Cisco working on the NCS 5500. This week again we have a short video taking place in the test series we started a few weeks back. Today we are working on systems based on Jericho Plus with external eTCAM, and we will verify that we can indeed program 4 million routes. But that will be after the break. We've done a couple of videos in the past on the FIB programming rate, and we are using here a very similar setup. At that time, we measured that we can push more than 30K prefixes per second. With systems and line card equipped with Jericho Plus NPU and external eTCAM, we don't need to distribute or manipulate the routes between LEM and LPM. We simply push everything in eTCAM. It's simple and fast. Only the multicast groups will go in LPM, while the MPLS information and the MAC addresses will be stored in LEM. First, I will use an NCS 55A2 mode SCS, and I will push both a full IPv4 and IPv6 internet view. We have a dozen of peers advertising multiple times the full table, and with the show DPA IP route resource CLI, I can verify the route distribution for v4 and for IPv6 with IP6 route. Then we check which resource is used to store all these routes, and we can see that indeed that's the external eTCAM, which is used for IPv4, 17% here, and also for IPv6, just 2%. We use exclusively the external eTCAM for these routes. Okay, let's try now to push 4 million entries. For this part, I will use a different router, a chassis with a 36x100 ASC line card, and I use a single BGP session advertising a lot of /28 prefixes. I've been a bit lazy here, I admit. It's not a very complex distribution. The router receives 4 million entries, which is the officially supported scale, but we know we can extend it in the future with software update if we have strong customer demand. The show DPA resource CLI this time is showing that indeed it's only /28 routes, 4 million of them, and it's also showing me that I don't have any errors in the programming to the hardware. Like I did before, I will use a show controller NPU resource to verify where my routes are going. And I see that I have indeed 4 million entries in external eTCAM, nothing in LEM, nothing in LPM. Yeah, it was a short one, but we have this request quite a lot in the past, so I hope it's useful. Thanks again for watching, and see you very soon. Ciao! Hey, this video is part of our lab test series. Today, Pratyusha Alluri will run some tests on a very large setup. She's a software engineer in Cisco, and she did set up 2 NCS 5508 routers, each fully loaded with 36 ports, 100 GB line cards, for a total of twice 288 ports. And she will run 2 big tests. First, loading the chassis with 28.8 terabits per second in both directions, with small packet size, iMix, IPv4, IPv6, then with and without configuration on the ports. The second test will use this very large testbed to demonstrate ECMP load balancing between multiple link aggregation bundles of 64 members each. Now I'll let Pratyusha running the test.
So this is the physical view. So these are two fully loaded 5508s, as you see, which are connected back to back with 100 gig AOC cables. Here I've just put two blocks. First block is to represent first router 55081, and the second one is the second router 55082. So the topmost, the port 0000, which is highlighted in black, connects to the traffic generator, and the remaining ports are wired back to back. That is, port 1 of line card 0 is physically cabled to port 1 of line card 0 on router 2. They are just mirror images. So this way, all the remaining 287 ports are wired back to back. This depicts how the VRF snake is set up on this test bed. So the numbering has been done in this slide. So number 1 represents the traffic that flows into the first router from the traffic generator through the physical link. And from port 0 of line card 0, the traffic gets switched through the fabric to port 0 of line card 1. And because it flows through two different line cards, the traffic flows through the fabric. This is to avoid local switching. From 2, the third part represented here is again the traffic that flows through the wire, that is port 0 on line card 1 of router 1 to port 0 of line card 1 on router 2. There are no features applied, so it's just MTU and the basic VRF config with IPv4 and IPv6 interfaces. So on all the interfaces, there are no QoS or ACL. So this is how the traffic generator is set up. Right now, we can start with 129 bytes, that is like 1 less than NDR. So what I'll be demonstrating now is bidirectional traffic. So if we look at the rate, it is set to 100% right now. I'll start the traffic at 129 frame length and show you that there is a slight drop. And then we'll increase it to NDR, that is 130. And again, go over the drop percentage to make sure there is zero drop. So this is bidirectional traffic. So right now, I've started in both the directions. So if I just focus on the bottom right here to show the drop percentage, dropped frame percent right here, it's about 0.4% in one direction and 0.4 in the other direction. So what I will do now is just stop the traffic, change it to 130, and then we'll monitor all the show commands on the router as well. And I've just cleared the statistics and started the traffic. So here on the left side, we see the PX and RX L1 rate percentage. That's 99.996 from the traffic generator. And right now the drop percentage is a 0 for both the streams. So I'll just go over the monitor interface star to actually show that the traffic is indeed flowing through all the ports of the system. Tag counters G and location 00. So this, I would think of it as a better view. So this tells us exactly how much traffic is on the ingress. So if you look at arrow marks here, so this is into the Jericho. This is the traffic that is flowing into the NPU. And from the NPU, if we scroll all the way to the bottom, this is the traffic that goes into the fabric. And then there is a command that we can look at the fabric statistics also. So show controller fabric plane all statistics. This actually tells us the in cells and out cells through each of the fabric cards. So this is the traffic that is on the fabric. And from the fabric, the reverse direction right here, this is the traffic that is again sent from the fabric towards the NPU. And also there was another test that was performed to actually run mini longevity kind of test with overnight snake traffic at 130 bytes. So I've highlighted that this traffic profile was run for about more than 9 hours and there are 0 drops. Along with that, there is power utilization capture too with both input and output, and same thing with respect to the CPU utilization. And there's no spike that is observed on the either the RPs or all the 8 line cards. We can do IMIX and say default IMIX. Let me show that to you. So this is the IMIX. So I can first change it to IMIX, and while we start the traffic, we can do the other testing. So this is the same line rate traffic with the index profile. So before I change the config to add features, I'll just switch it to IPv6. So that way there won't be any change in the config. So let me just start the IPv6 traffic. So right now the traffic that is flowing is IPv6 at line rate with 130 byte size. So I can just show you interface accounting to show that it is IPv6 unicast. And I can change it to show that there are drops at 129. Now I'll leave the traffic flowing for either one of these IPv4 or IPv6 at 130 byte size, and then load the configuration with features, and we can see that there is no impact to the traffic. So I have two versions of config saved on the box with features. So I'll just load that on the first router first. So there is traffic flowing on the traffic generator, and this will load, replace the current config with the config with ARCL and QoS on all the ports. So basically, when I run the snake test, the TTL value that is set, the maximum that we can set on the traffic is 255, right? So because I'll have to actually do more than 255 hops, I had used a profile command to change the TTL. So basically, this lets us match on a TTL value and set the TTL value on the router. So I've used that so that even before the TTL reaches 255, I basically increment it so that I achieve the entire 288 port snake. So the configuration profile that is loaded right now is ARCL and QoS on all the ports. This config is applied on both the routers, and the traffic that is flowing right now is IPv4 at 130. So as you can see here, it's the same as what we have seen earlier, no drops at 130 frame length. So the QoS, the ingress QoS right here is, I'll just show sample class map as well, is to match DSCP values and set the traffic classes. So I have 4 classes, and the fifth one is class default. So this is on the ingress. And on the egress side of it, these classes basically match the traffic class, which is set on the ingress. 2 of them are with priority, and the remaining are with bandwidth remaining. So this is the QoS configuration. Let me show you the statistics also. So everything right now is hitting the default class. And with respect to ARCL, so there are about 4,000 ACs for IPv4 and 4,000 for IPv6 as well. So these are the large ARCLs that are applied on all the ports. So now I'll switch to IPv6 for the same profile. So this is at 130 where there is no drop. We covered IPv4 VRF snake with and without features, and IPv6 snake with and without features. The other test I had here is with respect to the bundles. This is the slide to show how bundles are set up. So if we look at the ports that are highlighted in yellow, so those are 64 members, part of bundle ether 1. The ones highlighted in orange, that's another set of 64. Those are all part of bundle ether 2 and so on. So that way, yellow, orange, blue, and the peach color. So 4 bundles of 64 members each. And the remaining 31 ports are part of the 5th logical bundle, bundle ether 5. So this is how the bundles are laid out. So this is what I just spoke about, the 5 bundles. So now the traffic that I'll be starting is first IPv4. So these are all BGP prefixes, and the total number of flows that I'm sending are about 100K flows. The distribution is per source IP and destination IP addresses. The hashing can also be obtained based on the source port and destination port, but this test that I've set up is based on the source destination prefixes. In order to see how the traffic is getting load balanced, we'll go over two things. One is the ECMP to see the traffic split on all the 5 bundles, and then we'll look at per member. So these are the 5 bundles, and we see the in and out. It's almost 16.89 on all the 5 bundles. And same thing, and this monitor interface of all the members of line card 1, because they're all part of bundle Ether 1. So this will display the lag, how the traffic is hashed across the bundle members from the same bundle. So I'll just quickly switch to IPv6. The drop again is 0. Let me expand this just a second. So the variation here is based on the source IP address and the destination IP address, and I have a total of 25,000 rows. So V6 prefix is also reachable via 5 bundles, and I started the IPv6 traffic, and this is the ECMP across 5 bundles. So these are all the members from bundle Ether 1. So the drop right here is a real-time, it's a variation what Spirent does, but once I stop the traffic, ideally it should all go back to 0. So this is what we can look at, 0 drop count.
Thanks, Pratyusha. Also, thanks to you for watching the video. Don't hesitate to subscribe to the channel and use the comment section if you have any question. See you soon. Hi, Nicolas Février here. I'm a TME for the Service Provider Business Unit at Cisco, and more precisely, I'm working on NCS 5500 products. This video is another episode of our lab series, and you can take a look at the test we recorded so far in the playlist. Also, in the description, you will find a link to xrdocs.io where all the details will be available. In the last episode, my colleague Pratyusha demonstrated with a large test bed what is the NDR of a 36 by 100 GB SC line card powered by Jericho plus ASICs. NDR stands for non-drop rate, and it does represent the minimum packet size you can transmit on all ports, line rate, simultaneously. Let's try to dig a bit deeper to understand what's behind this NDR number, just after the intro. Having 2 chassis and 288 ports wired is a very impressive setup, but you can actually demonstrate the same thing with just 18 ports and 2 NPUs. We wired a full line card, that means a snake of 36 ports, but half of them would have been enough for the demonstration. In this topology, we make sure that traffic is not locally routed and always transiting through the fabric. Today we will explain you why you reach a line rate with packet size above 130 bytes, and also why you will have a short dip between 230 and 278 bytes. But we won't have drops at this packet size if you slightly reduce the interface bandwidth. The last test will demonstrate it's happening at the NPU level, and it's not a port limitation. If you do the math, we have 9 ports per NPU, and each Jericho Plus can treat 835 million packets per second. That should give us 92.7 Mbps per 100 GB port. But that's not what we measure. If we generate traffic at 129 bytes, just below the NDR, we receive 83.5 million packets per second. So how can we explain this inconsistency? A snake topology is actually not ideal to measure with precision the NDR. On these routers, you have 9 ports per NPU. Each NPU is made of 2 cores, so logically, one core will have 5 ports, while the other will have 4. So this show command can be used to display the port allocation. 100 GB 0600 is NPU 0 core 1, same thing for port 1, and port 3 is assigned to NPU 0 core 0. With a snake, the NDR will just show the lowest performance between core 0 and core 1. Each core is capable of 417.5 million packets per second. Divided by 5 It's 83.5 Mbps per 100 GB port, which is indeed what we measured. The performance of the 4 other ports would have been 104 million packets per second, but it's something we cannot demonstrate with this topology. Now let's take a look at this dip between 230 bytes and 278 bytes. First, let's see if we can reproduce that in our lab. We start with 229 bytes per packet, no drop. Then we try with 279 bytes, and the same. But indeed, with 278, we notice drops on the traffic generator, and it's also the same for 230 bytes. To understand this behavior, we need to talk about the way packets are split in cells when they are transmitted to the fabric. The cell size is variable, from 64 bytes to 256 bytes. And we don't support the transport of multiple small packets in a single cell, something we used to call superframing in the ASR 9000 world. Internally, the system will add headers that will be used in the pipeline by the packet processor and the traffic manager. Total, it creates an overhead of 27 bytes. That's why a 229-byte packet will be transmitted in a single cell, while a 230 bytes packet will be split in 2 cells. While we increase the packet size, the PPS is getting smaller and the impact is no longer noticeable after 278 bytes. That explains the 8% impact on the line rate performance, but in the lab we have seen sometimes that it can go up to 20% or more, and it's because of a cascading effect. We can check in the graphical show command what are the reject reasons of the ENQ discarded packets. It displays FADT. It's Fair Adaptative Tail Drop. Take a look at the blog post to understand more about this mechanism. After several seconds, the loss increases and we can see now IDR DRAM rejects in the show commands. We verify with these other show commands that indeed we have drops related to the DRAM. What we experience here is really only relevant in a lab environment where we are able to maintain this 900 gigabit per second of constant stream with the same packet size. Let's see the step of this cascading effect. Packet is received, but fabric is congested. It generates a back pressure message to the ingress NPU, which will now evict the particular VOQ to the DRAM. Since all the generated traffic is pushed to DRAM, we eventually saturate the links to this external buffer. And that's the IDR drop reasons we are seeing here. I want to insist one more time that we are providing all these details to explain what can be seen in lab. In no manner it represents a realistic scenario, simply because you cannot get more than 90% of this particular packet size on all the ports of the NPU at the exact same moment. I said 90%, so let's try to see if the problem is reproducible with 256 bytes and 90% line rate. So we start with line rate, 256 bytes, and we check that indeed we have drops. Okay, now reducing the traffic generator to 90%, no drop anymore. In this last test, I changed the configuration, and now I directly route the port 0 and the port 35. Now they are both part of the same VRF1. So we verify that we don't have any packet size limitations between these two ports only. We start with 64 bytes packets, no drop, no packet move to DRAM either, and we show the same with 256 bytes packets, which is the middle of the deep range that we detailed earlier. Same results, no drop. Okay, so that concludes this test on the packet size. Let's hope it was informative. Thanks for watching and see you soon. Nicolas Février here, TME for Cisco's NCS 5500 team, among other things. Today I have a short video for you, and this one is an addition to the lab series we initiated a few weeks back. Remember, the purpose is to execute some tests in our labs, record and present the results, and in the process provide more internal details on the NCS 5500 platform. Today we are testing the fabric card removal and its impact, and I will tell you more just after the break. First, you remember that fabric cards are directly connected to the line cards without mid-planes, something we call an orthogonal architecture. And fabric cards are also connected to the fan trays. The consequence is you need to eject the appropriate fan tray to be able to manipulate the fabric card. And you can see in the config guide that we only support this mode of operation during a few minutes. Some important note here: we can operate with a faulty fan tray for a very long time. The two remaining ones will speed up to compensate. But we don't support a situation where we remove the fan tray and don't guarantee the sealing of the chassis for more than a few minutes. It's an important distinction. For the following test, we will shut down electrically one of the 6 fabric cards to simplify the process, and we will check the impact on performance. We mentioned before that fabric cards are directly connected to the line cards. More precisely, all forwarding ASICs, or NPUs, are directly connected to all the fabric engines. So when you remove a fabric card, you potentially impact the forwarding capability of all the NPUs equally, whether you have 1 line card, 8 or 16 inserted in the chassis. It will be the same impact per NPU, simply because internally it's a full mesh and everything is connected to everything. It will not impact the performance in terms of packets per second, but potentially in terms of bandwidth, so in gigabit per second. Why do I insist on potentially? Some line cards are capable of being line rate on all ports with 1 fabric card less, but some others will have a slightly degraded performance when used with just 5 fabric cards. Let's be very clear here. Like all the things we are sharing in this test series, it's essentially a lab issue. If I show you that we have 92% of the forwarding capability in some cases when losing a fabric card, it's not something you can recreate in a production network. The scenario when you have more than 92% load in average on the 900 GB ports of an ASIC is unrealistic. That's what I call a lab thing. So we are detailing in the blog post the N+1 support for every existing type of line card. Now, back to our test. We will run it on an 8-slot chassis with a 36x100 SE card, powered by 4 Jericho Plus. We will run the test with 1500 byte, 500 byte and 130 byte packet size, and we will see what's happening. Keep in mind we are using also a snake topology, which will increase the impact because of a loop effect. To calculate what will be the consequence of losing 1 fabric card, we will need to understand first the available bandwidth. For each ASIC, we have 900 GB of network traffic and 1200 GB of fabric bandwidth. But internally, we impose headers to this traffic, so what is actually available on the fabric side is 998 gigabit per second. Losing 1 fabric card will reduce it to 832 gigabit per second, which is 8% below the nominal 900 GB that we need for line rate. Now let's see what we experience in a lab. Starting with 1500 byte packets, we see around 11% of drops on the traffic generator. On the router itself, we use a graphical view of the ASIC, and particularly we check the ENQ discarded reasons. We see IDR DRAM rejects, resource errors, fair adaptative discards. Check on the blog post to get more details on these messages. Now we reduce the packet size to 500 bytes, and we clear the statistics. This time we see between 8 and 10% of drops. Finally, let's use the NDR packet size for this line card, which is 130 bytes. We can see from 12 to 16% now. Back to the router one last time, we will check the IDR DRAM drops, and we can see quite a lot of full DRAM rejected packets. And we are seeing drops because of DRAM block condition. It occurs when we exceed the bandwidth the DRAM interface can handle. It's exactly the same situation I was describing last week in our NDR test video, when the packets are split in cells, exceed the fabric capacity, generate a back pressure message, then evict the video queue to the DRAM, and finally saturate the DRAM capacity, something around 450 GB read and write simultaneously. That explains why we have slightly higher drops than the 8% we got from the math. That's all I have for today. Next week, we will push 4 million IPv4 routes into the FIB. Thanks for watching. Please leave your comments and a question below or in a blog post. Ciao! Today we are playing with the NCS 5500 commands. You know, the route processors, the power modules, the fan trays, and the system controllers. Just after this. That's already the 6th video we are doing in this category, the lab testing. If you missed the other episodes, we extract test cases from customer POCs, proof of concept, we execute them in our labs and we present the results. You can use it as a comparison point when you are performing a validation of the product, or even better, you don't even need to do it. Sometimes it will be a very large or complex test beds. Some other time it will be something much simpler. So far, we tested fully loaded snake topologies and measured non-drop rate numbers. We tested the fabric redundancy, the FIB programming speed, the BGP flow spec operation, and much more. The end goal for us is to speed up your validation process and show you the product capabilities. Today we are testing the NCS 5500 commands. That means the route processor, the system controller, the power supply, and the fan tray. All of them are operating in high availability mode. You can remove one without creating any impact on the service. We'll check the traffic generator at the beginning of the test, and we will take another look at the end. Hopefully, we'll verify we didn't lose any packet. Also, thanks a lot to Punit Kalra who prepared and recorded this test. We are using a 7.0 image. You can see that in the RP and the line card in slot 4. The product we are using for the test is an NCS 5500 8-slot chassis with 36 by 100 gigi SE line card. That's the one based on Jericho Plus with external eTCAM Optimus Prime. The ports are connected in snake topology using static routes in VRFs. It's a chassis, so we have 2 route processors here in active and standby state. Also, we have 2 system controllers used for all internal communication inside the router and responsible for the health monitoring of the different components. No concept of active standby here. They are both operational from an operator perspective. We have slots for 8 AC power supply modules, but only 4 are operational at the moment. They can provide up to 3 kilowatts each. On the back, we have 3 fan trays. You can see they are V2, that means they work in pair with fabric cards of 2nd generation, and they can support 400 gigi line cards. In admin mode, we check the power supply modules, and we can see how they convert the 2010-ish volts into 12 volts used by the internal components of the chassis. Still in admin mode, we have the visibility on the 6 fans of each fan tray and the round per minute statistics. We quickly check the traffic generator and we can see 0% packet loss. Remember that frames delta can only be checked after stopping the traffic. Let's start the redundancy test with the route processor. The RP0 is active, RP1 is standby. We extract manually the RP0 on the left. Logically, we lost the console and we need to reconnect on the other console port of RP1. On the show platform, we will see RP1 present and in active state. Let's reinsert the RP0 and we fast forward the next 4 minutes. And we see the RP0 completing the booting process, and now it is in standby state. We quickly check the XR console and no traffic loss. Let's move on to the second part of the redundancy test with the power modules. In admin mode, we check the PSU installed. In group 0, all modules are disconnected, and in group 1, the 4 PMs are in OK state. In front of the chassis, on the bottom part, we eject the PM5 using the lever. Now a show platform will display we have PM5 in state failed. If you pay close attention, you will notice we actually manipulate the PM4 on the video, but it's just for the illustration and we didn't want to give you 15 minutes of CLI. So we reset the power modules. With the same show command, the PM5 is back to operational state. Here again, a quick look at the traffic generator graphical interface and no packet loss. Third part of this video, we now go to the back of the chassis and we will test the system controllers. No concept of active and backup on these ones. They are both in operational state. We extract one of the controller, and with the same show platform CLI, we verify that we only see one present. And we reinsert this SC back in its position. We fast forward this sequence again, and it will take a bit less than 8 minutes to come back to nominal state. Here again, another quick look at the traffic generator where we see 0% packet loss. Last test for today, the fan trays. We have 3 of them in a modular chassis named FT0, FT1 and FT2. You can see that we are using V2 models here. They are working in pair with Fabric Card V2, and they are mandatory if you consider inserting 400 gigabit Ethernet line cards. But of course, they are backward compatible with Jericho and Jericho Plus based line cards, like it's the case in this demo. You have the detailed view of the speed the 3 dual fans composing each fan tray are operating. Let's go ahead and eject the fan tray 0. Now you can see the fan cards behind it. Of course, FT0 disappeared from the show command output and also from the show platform output. We put it back in place and very quickly FT0 is seen in show platform, but it will take more time to have all the individual fan speed counters collected and displayed in the admin show and fan CLI. We check one last time the drop counters at the traffic generator level, and there are none. Okay, it's time to conclude. We started the traffic in a snake topology and we extracted the active route processor, 1 power module, 1 system controller, and 1 of the 3 fan trays. And we didn't lose any packet. If you have any specific test in mind you would like to see executed, please let us know. You can use the comment section of this video or in the XR Docs article. Thanks a lot for watching, stay safe, and see you in the next one. Ciao.